Our goal for this video is to give a bunch of examples of representations of common groups from first semester abstract algebra. So let's go ahead and start by recalling the definition of a representation. So let's suppose that V is a vector space over C, but really we could do this over any field. But generally, elementary group representation theory is done over C, and that's because it's easiest to do it over something called an algebraically closed field, and C is maybe the simplest one of those to deal with. And then we also want to suppose that G is a group. And in fact, as we move forward, we're almost only going to work with finite groups. So we'll look at the representation theory of finite groups over the complex numbers and complex vector spaces. Next, a representation of G over V is a homomorphism phi from G to GLV. So recall that GLV is the space of invertible linear transformations from V to V. And then next, we say that the degree of this representation is equal to the dimension of the underlying vector space. Furthermore, if the dimension of V is equal to n, which is less than infinity, in other words, we have a finite dimensional vector space, that's another thing that we're generally going to impose, then phi really goes from G to GL in V. And let's recall that this is the group of n by n invertible matrices with coefficients in the complex numbers. Okay, so now that we've got this definition recalled, let's go ahead and look at some examples. So we're going to run through like cyclic groups, dihedral groups, symmetric groups. We're going to look at the quaternions, and that'll give you guys like a nice feel for what these representations look like. Those are like the most common groups that you work with in an abstract algebra course anyway. So we won't check that any of these are homomorphisms, but we will describe what the homomorphism does to the generators of the groups, so it's pretty easy to check from that point. Okay, so the first case that I want to look at is Zn, and I want to look at a one-dimensional representation, kind of a standard one-dimensional representation, as well as a standard two-dimensional representation. So for the standard one-dimensional representation, I need a homomorphism from Zn to GL1C, but GL1C is just the group of invertible complex numbers. In other words, the group of non-zero complex numbers. And now, here's what I can do. I can take the generator, which this is an additive group generated by 1, and I can send it to the nth root of unity. So that's going to be e to the 2 pi I over n. Great. And now you can check that this is a homomorphism. It essentially takes this additive group and turns it into a multiplicative group. And in fact, we don't have to take it to this root of unity. We can take it to any nth root of unity. So this can go to e to the 2 pi k times I over n. For like any k between really 0 and k minus 1 might give you something different. Now, some of those will not be injective homomorphisms, which means it won't be kind of a nice representation, but we're not going to worry about that so much. Okay, great. Now, let's deal with this one that I have in white chalk, and then we can write down what happens to an arbitrary member of Zn. So that, in this case, we have for some arbitrary member from Zn. And so we're thinking of that as an equivalence class, modulo n. We'll have phi of m is equal to e to the 2 pi m I over n. And that's just by the fact that this is a homomorphism. Okay, fantastic. Now let's look at a two-dimensional representation of Zn. And for that, we're going to look at something which is a nice, really example from linear algebra that you might have seen before. So this is going to go to GL2C. In other words, we want to represent the elements of Zn by 2x2 matrices. And we're going to do that in the following way. So again, I'll see what happens to the generator. So again, it's generated by 1 as an additive group. Now this is going to go to cosine 2 pi over n minus sine 2 pi over n, sine 2 pi over n, and then finally cosine 2 pi over n. Great. And then furthermore, we can easily see what phi of m does. So if we have m, which is an arbitrary element from Zn, so that's an equivalence class, then phi of m will go to the same thing, except we'll have 2m pi everywhere here in the trig function. Great. Now maybe I want to think about what this is actually doing. So what you want to think about here is we've got some two-dimensional plane, and this is rotating the axes of these two-dimensional plane 1 over n in the counterclockwise direction. So in other words, it's rotating the axes like this, where this angle right here is 2 pi over n. Good. And now you might notice here that all of these are real numbers. So in fact, this is a two-dimensional real representation. So we don't even need the complex numbers in this case. You can kind of upscale it to a complex representation, but this is actually a real representation. Okay, great. So now let's go ahead and clean up the board, and then we'll look at representations of the dihedral group. Okay, so now we're going to look at representations of the dihedral group. And this is an obvious extension of representations of a cyclic group, because this R right here, which is the rotation, generates a cyclic group of dn that's isomorphic to zn. So it's nice to kind of build a representation from dn off of a representation from zn. So the way that we want to think about this is the fact that dn is the symmetry group of a regular n-gon. Now we're going to put that regular n-gon in the plane and really see what the action of these symmetries does to the entire plane. So here we're going to have phi going from dn to, we'll look at a two-dimensional representation. So this will be GL2C. In other words, we want to represent these elements by 2x2 matrices. And we'll do that by taking R to that rotation matrix that we had in the cyclic case. So it's going to be exactly the same rotation matrix. So we'll have cosine 2 pi over n minus sine 2 pi over n, sine 2 pi by n, and then finally cosine 2 pi by n. And that's what happens to the generator R. But if you had R to the m power, in other words, you know, a rotation m clicks around the circle, well, then you would just put an m everywhere here. So that would be what the R to the m element looks like. Good. And now let's see what phi of s is. So phi of s under this setup will be the following. So it'll be 1, 0, 0, minus 1. And now you can check that phi of r and phi of s maintain the same commutational relations as r and s given up there. And furthermore, it's kind of obvious that phi of r to the n will be the identity matrix, and phi of s squared will also be the identity matrix. Okay, so now I want to think about the geometry of this thing. So phi of r is doing the same thing that the rotation matrix did in the last example. That is, it is taking the axes and rotating them by 2 pi over n radians around. So that is what our r is doing. So I'll just put phi of r there. Great. And then let's see what phi of s is doing. So it's fixing the horizontal axis. Maybe we could call that the x-axis. And then it's taking the y-axis to the negative y-axis. So maybe I'll write that just in the following way. So that's my phi of s. It's doing that kind of thing right there. And now if you look for what's happening to maybe sr to the m, well, you would just multiply kind of the appropriate powers of these matrices in order to get that. Okay, so now I want to look at one more two-dimensional representation of the dihedral group. Notice this one doesn't take into account anything about complex numbers, but we could have one with complex numbers given as follows. So we have phi of r is equal to e to the 2 pi I over n, 0, 0, e to the minus 2 pi I over n. So as we'll see, this is actually a diagonalized version of this rotation matrix. This will be something that we play around with later. And then phi of s will be equal to 0, 1, 1, 0. Okay, so now I kind of want to think about the geometry of this. So we still want to think about a plane, but we really have to twist our minds, because each axis on this plane is a complex axis. So each axis is a complex plane. So let's see what's happening. This rotation matrix, notice it doesn't do anything to the larger two-dimensional complex plane, but it does twist each of the axes. So I like to think about this thing as maybe doing some rotation inside each of these axes. So that's what phi of r would be. Great. And then what is phi of s doing? Well, that's a little more clear cut in this case. Notice that phi of s is permuting the larger axes. So maybe we could say it's a reflection about that axis right here. So I'll maybe put these arrows right here to say that's what phi of s is doing. Okay, great. And as we'll see later, there's a connection between these two representations, but that's kind of a goal for another video. All right, I'll clean up the board and we'll look at the quaternion group. Okay, now we're going to move on to some representations of the quaternion group. So let's recall that that's a non-abelian group of order 8. There are two non-abelian groups of order 8. One is D4, the symmetries of a square, and the other one is Q8. So we took care of the representation of D4 on the last board. So Q8 has the following elements: plus minus 1, plus minus I, j, and k. And I've put hats over them because I want to distinguish the I from the square root of minus 1 in the complex numbers. And then the multiplication is so that I squared equals j squared equals k squared equals -1. Let's maybe remind ourselves of that. And then the looping action happens with the rest of the multiplication. So in other words, if we follow the direction of the arrows, we pick up a plus sign. And if we reverse the direction of the arrows, we pick up a minus sign. So you want to read this as I times j equals k, j times k equals I, k times I equals j. But now j times I is negative k because we're going against the arrow. So I'll let you guys look up. I've got a whole video on the quaternion group if you want to check that out. Okay, so now we're going to look at two-dimensional representations of the quaternion group. So that means we need a homomorphism from Q8 to GL2C. In other words, we need to put it into 2x2 complex matrices. And the way that we're going to do that is as follows. So I'll leave it to you guys to think about what happens to plus minus 1. Spoiler alert, it's just plus minus the identity matrix. There's not much of a choice there. So now we want to see what happens to I, and thus we'll also know what happens to minus I because it'll just be -1 times the output matrix. So we really only need to look at what happens to I, j, and k. In fact, we only need to look at what happens to I and j because since k is equal to I times j, we can construct that out of that, but we'll put them all down. Okay, so phi of I will be equal to I, 0, 0, minus I. Good. And I want to make sure I put an I hat over here. So this is the I hat from the quaternion group, and this is the square root of -1 inside the matrix. Okay, good. And then let's see what phi of j hat is. So phi of j hat will be the matrix 0, -1, 1, 0. Great. And then from that, we can see phi of k hat equals 0 minus I minus I 0. Good. And now I'll leave it to you guys, but you can look up, and there's actually a nice four-dimensional real representation of the quaternion group that can be essentially built out of this. Oh, this should be just I's instead of I hats because those are complex numbers. And it can be built out of this by the two-dimensional representation of the complex numbers. So you can embed the two-dimensional representation of the complex numbers into this two-dimensional complex representation of the quaternion group to get a four-dimensional real representation of the quaternion group. So there's a bunch of places to find that on the internet if you're interested. But I think this is going to suffice for our purposes. Okay, so this is the classic two-dimensional representation of Q8. So now what I want to do is look at a more general one, of which this is a special case. So let's go ahead and let alpha and beta be complex numbers. And I want to say that they are any complex numbers satisfying the following equation: alpha squared plus beta squared equals -1. So obviously there's a bunch of complex numbers that satisfy that type of equation. And so these are just any two of those. And now we can actually build a representation of Q8 out of those two numbers. So here we have Q of I hat is going to be sent to alpha beta, and then beta minus alpha. And then Q of j hat actually goes to the same thing. So that's 0, -1, 1, 0. And then phi on k hat needs to be the product of these two matrices, you know, by our definition for the quaternion group. So that's going to be equal to beta minus alpha minus beta. Okay, good. So now there's something that looks like a way more general two-dimensional representation of Q8. All right, so I'll go ahead and clean this up. Then we're going to look at some representations of Sn. Now we're going to look at the most basic representation of Sn. So the representation theory of the symmetric group is very, very rich. There are several very large books written just on the representation theory of this group. And maybe in later videos, we'll look at something a little more deep than this. But right here, we're just going to look at the standard representation. And so the standard representation is a homomorphism from Sn to GLN C. So in other words, it's going to take a permutation on the group of n letters and send it to an n by n matrix. And in fact, it's going to send it to something called an n by n permutation matrix. So what I want to recall really quick is that there's this standard basis of Cn given by E1, E2, up to En. And so those are the standard basis vectors. And so what I'm thinking about here is E1 equals 1, 0, 0, but it's really like a column vector, so I'll put a transpose there, but I don't want to take up so much room. And then E2 will be 0, 1, 0, 0, 0, and then EI will have zeros everywhere except in the ith component, and in that component there will be a 1. Okay, so now the standard representation takes some permutation sigma and sends it to the matrix whose columns are described by the action of sigma on these basis vectors. So it'll be E sigma 1, E sigma 2, all the way down to E sigma n. So let's look at a couple of examples of this. So maybe the first one that I want to look at is sigma, which is the 3 cycle 1, 2, 3 inside of S3. So notice this cycle notation tells us that sigma 1 equals 2, sigma 2 equals 3, and then finally sigma 3 equals 1. So that's how we read this cycle notation. And so what that tells us is that phi of sigma in this case, so that's going to be E of sigma 1, so that's going to be E2, and then E sigma 2, so that's going to be E3, and then finally E1. But now putting those back into standard basis vectors, that's going to be 0, 1, 0, 0, 0, 1, and 1, 0, 0. So that is the permutation matrix associated with this 3 cycle. That's kind of the same thing that you do for all of these types of examples. All right, I'll clean this up and we'll look at one more example. Okay, so for our next example, let's look at sigma, which is 1, 2, and then maybe 3, 5, and let's say that this is in S5. And so what that means is that sigma 1 equals 2, sigma 2 equals 1, sigma 3 equals 5, sigma 5 equals 3, and then sigma 4 is itself because that's not represented in this like cycle notation here. Okay, good. So that means that phi of sigma is going to be the permutation matrix resulting from taking the identity matrix really and permuting the columns the way described over there. So notice this is going to be E2, E1, E5, E4, E3. Good. So now we could write that out. So that's going to be 0, 1, 0, 0, 0. So that would be the first column because that's E2. Then we have 1, 0, 0, 0, 0. So that's the second column. That's E1. And now so on and so forth. 0, 0, 0, 0, 1, 0, 0, 0, 1, 0. And then finally 0, 0, 1, 0, 0. Great. So that would be the permutation matrix associated with this permutation. Okay, great. So I'm going to clean this up, and then we're going to look at a very, very simple but important representation of Sn. We just got done looking at the standard representation of Sn. The next thing that I want to do to finish this video off is look at something called the sine representation of Sn. So it's going to be a one-dimensional representation. So in other words, it's a homomorphism from Sn to the multiplicative group of complex numbers. In other words, non-zero complex numbers. And you probably saw this representation in abstract algebra class, but it wasn't called a representation. So it's given in the following way. So we have phi of sigma equals -1 to the SGN of sigma, in other words, the signum of sigma. And this is defined in the following way. So SGN of sigma is equal to 0 if sigma is in the alternating group. In other words, it's an even permutation. It can be written as an even number of transpositions, and it's equal to 1 if sigma is not in the alternating group. So while this is a very simple representation and a homomorphism that you probably saw in abstract algebra, this representation plays an important role in the theory of Sn. Okay, so I think that's a good place to stop.